Data Analysis Part 6. Joint probability and using mathematical probability to make predictions and statistical inferences, especially using Bayes' rule. Hello everyone, welcome to Part 6 of this data analysis course. So far in this course we've looked at some fundamental ideas in data analysis, descriptive statistics, and designing experiments to be as useful as possible. We've started also to look last time at probability theory, so mathematical probability, and what did we get to? So we looked at the notation of probability, the laws of probability, the meaning of probability. This time we need to get to mathematical rules for dealing with probability of two things, so that we can use one of them, some data that we've observed, to draw probable conclusions about the other thing, or to make statistical inferences. And to do this, we'll introduce the concepts of conditional probability, joint probability, the principle of indifference, very important, and Bayes' rule. So we will do that. Because this is a video lecture, I don't need to recap in detail what we looked at last time. I will simply recap that we said we're considering probability as a degree of belief that some statement is true, so that's the logical interpretation of probability, where we're going to end up with probabilities from 0, I'm completely certain something is not true, on a sliding scale up to 1, that I'm completely certain a statement is true. We introduced in section 4.3 the mathematical notation of probability, and we talked about the laws of probability in section 4.4, also called the Kolmogorov axioms. And we said that we can get these laws of probability either from intuitive claims about how we think probability should work, we can agree that's where they come from, or we can do what Kolmogorov does and just says these are some laws, let's work out what system applies if they're true. Or we can do what Richard Cox does, and we can say, following his argument in the algebra of probable inference, we can say if we believe some certain things, certain statements have to be true about our degree of belief, then we think the following laws should also be true. Anyway, so you get the laws of probability, and we can do some manipulations with them based on the notation of probability. Great, so where do we get to? The intersection of two events, special cases of probability, certainty, and independence. So, section 4.5, this is worth reading. So, the fundamental task in scientific data analysis is to describe the relation between the probability of one event and something else that we don't know about. So how does our degree of belief that some possible conclusion is true changed based on the data that we have? This requires something called joint probabilities, and so some notation you need to know for this. If we have events A and B, the occurrence, both of them being true, or the occurrence of both events, is called their intersection. The notation for the intersection of events A and B for the probability of this is P brackets A intersection B, where the intersection sign, if you need this in Microsoft Equation Editor, it's cap, or in other words you type \cap and you get the intersection sign. It looks like an N, but it's not. The symbol isn't exactly an N. You want, in Equation Editor, \cap. So the event A intersection B contains only the outcomes which are in both event A and also event B. And this is you need to know this can happen in a few important different ways. Equation 4.5a describes mutually exclusive events which have an empty intersection. There are no outcomes which are in both. The example is when rolling a die, getting a 1, 2, or 3, intersection with another event, getting a 4 or a 5, that has no outcomes in common. When the probability of the intersection of two events is different from this, when it's, as in equation 4.5b, we have a situation second important case of independence between the events. So independence, so A, B, and C, the definition is in the equation, are independent events whenever the probability of the intersection of A, B, and C is equal to just the straight multiple of probability of A times probability of B times probability of C. And this has a ... because you can see how you would add additional events D and E, etc. It's just that the intersection is the straight multiple of the independent probabilities. So there are three important ways that you need to know events can be related. You need to know that there's impossibility. This is what we see in equation 4.5a. Impossibility means there are no mutual outcomes. So given that you know the outcome of rolling a die is 1, 2, or 3, then it's impossible for it to be a 6. Conversely, you have certainty, which is closely related. Given the outcome of a die is rolling a 6, then the probability, my degree of belief in the statement, well, it was a 4 or a 5 or a 6, that's certain, that's definitely true. Impossibility and certainty are obviously easy to understand. Independence is the other case. It's where independence is when you get no information about a second event from a first event. So given in the mathematical example that's often given that you've rolled a 6 on a fair die, your probability of the outcomes of the second roll remain equally believable. Or to put it another way, independence happens when knowing the outcome of knowing that one event has happened tells you nothing about whether the second has happened. So, for example, rolling a 6 on one die provides you no information about the statement, it is raining, to give you an example of something where there's obviously independence. Why do we need this notation? Well, because in doing statistical inference, the mathematical thing which we do, which is also the thing that we do naturally when we reason about subjects, is we condition on events or statements. So conditioning means assuming that one thing has happened or is true, and then how does that change my degree of belief in other things? There are two possibilities. As I said, these are related. These are the important cases we just looked at of impossibility and certainty, which are really one case, and independence really the other case. These are also written up in equations or comments 4.5c and d. So you can get no new information, no relevant information about event B from event A. In that case, they are independent. The standard example, given the roll of a fair die, that tells you nothing about the outcome of the second roll or about the statement it's raining or not outside. On the other hand, if there is new relevant information, then your probability of B changes, and you say that your new probability of B is conditioned on the information that event A occurred. We need an equation for this, which is 4.5e, and we need to describe the definition of this. It's worth saying, equation 4.5e describes conditional probability. Now, depending on which textbook or which type of probability you're working with, this might be considered a fourth law of probability. So the mathematician, this guy Definetti, considers conditional probability equation 4.5e to be a fourth law of probability, or a fourth axiom. And he says that you can derive this along with the others via the arguments of Cox's theorem. The Kolmogorov system of probability considers this not to be a fourth law of probability, but to be a definition of the way we believe some probabilities behave. So there's some dispute about what conditional probability is fundamentally. but nonetheless you get the same notation. And what is the meaning of the notation? We have the notation probability of B given A, or in other words, probability of, in brackets, B vertical line A is the conditional probability of B given A. Very often you might find that this might be written in a slightly more complicated way, to write down explicitly that we have extra background information about the problem in hand, and you might see it written down that we know not just A, but background information I, in which case you might see this thing written as probability of B given A, comma, I. That's just a way of making very clear that when I'm doing statistical inference, I usually have background information about the problem, as well as some knowledge of the outcome of event A. Anyway, so you've got your conditional probability of B given A. It's defined as, and this is essentially a fourth law of probability, at least if you believe in definity. The conditional probability of B given A, it's the probability of the intersection of B and A divided by the probability of A. Great, okay. Now, equation 4.5e for conditional probability does satisfy the intuitive rules which we need to apply in the three special cases of inference, which are impossibility, certainty, and independence. It's a law, so it's also true in the more complicated cases where there is some other general relation, but let's just first of all prove that conditional probability does obey intuitive rules for the necessary cases which it must intuitively apply for. So conditional probability is defined. Probability of B given A is the probability of the intersection divided by the probability of A. So first of all, impossibility. When we had mutually exclusive events, example, outcome of rolling one die being 1, 2, or 3, or in the other case 6, well, if we know it's 6, then there's 0 events in the intersection, so the probability of the intersection is 0. The probability of the denominator, in this case rolling a 6, is something. The probability of rolling a 1, 2, 3, given that you rolled a 6, is of course 0, simply because the intersection was empty. Putting it the second way around, certainty, probability of rolling either a 4 or 5 or 6, given that you're told you rolled a 6, that's obviously certain, or it gives you probability 1. In this case, the probability of the intersection, rolling a 4, 5, 6, or a 6, is the same as the probability of rolling the 6, the denominator. So you take the ratio and you get 1. In the case of independence, you have this third possible way of writing this down. The probability of getting a second roll with outcome something, let's call it the outcome y subscript j, which is your second roll y has any outcome 1 to 6. Your probability of your second outcome, given that your first die roll was a 6, that plugging its values into the equation for conditional probability, well, they are independent, and the way of correctly manipulating this is that given they were independent, you've got 1/36 for the probability of the intersection, and of course 1/6 for the probability of rolling a 6 on the first die. Result of that is that your conditional probability, when you have independence, your conditional probability of the second outcome of rolling a die, rolling the die the second time being a 6, that's still a 6th, regardless of the fact you've been told what the first roll gave you. That is, of course, from the definition of independence. So if that sounded like a circular argument, it was. By definition, these things are independent when this is true. Good. Now, let's discuss a more general case of conditional probability than the special cases of impossibility, certainty, and independence. In order to discuss these, we're going to use the following sort of Venn diagram, which shows overlapping areas to describe the relation between events. Remember, in the last lecture, I said it was important to note that it's simply a useful fact that the laws of overlapping areas, the mathematics obeyed by overlapping areas, obeys the same laws as the mathematics of degree of belief probability. And therefore we can visualize probability in terms of one of these area diagrams. That's the correct way around to think of it. There's nothing magical about area in some metaphysical space which causes probability degree of belief to obey these same relations. It's because in both situations we could write down the same mathematical laws to describe the relations. So what you will hopefully easily understand is that this describes a intuitively correct way of doing conditional probability for our degree of belief in some conclusion. So the situation is it rains on 10% of days. All of those days are among the 50% of days that it is cloudy. This is in Cambridge, let's say. So therefore, the information "it is cloudy" makes the other 50% of days, clear sky days, impossible. But it doesn't tell us anything more about the belief of cloudy and raining, or cloudy but not raining. So we can, however, make some progress using this kind of this cloud-rain Venn diagram. So in this diagram, units of equal area correspond to statements about which I have equal belief, and area is proportional in some way to the amount of belief that I have. Now, if we combine just the ideas that we have so far of being equally certain in outcomes, but not saying anything about them other than they're equally plausible, and impossible, now gives us an equation for conditional probability, which is good enough for learning in a special case. So let the event A be "it is cloudy," and the event B be "it is raining." Of course, it's also cloudy. In the information I already have, my probability of A on some unknown day that it is cloudy was 0.5. We knew from the background information the probability of the intersection of A and B, that it was both raining and cloudy, was 0.1. Plugging these into the conditional probability equation, your probability that it is raining given that it's cloudy, P of B given A, comes out as 0.2. But that's just making use of the fact that some things became impossible when you were told that it was cloudy. You ruled out the possibility it was not cloudy and therefore definitely not raining. However, you said nothing about the relative weighting of it being rainy and cloudy, or not raining but cloudy. In general, we can make quite a bit of progress in data analysis simply by exploiting the fact that some things become impossible based on data that we've received. So let's look at a second example of that, just because it's going to let me talk about some things I found interesting after this. So there's this example 4.5g. What is the probability, or your degree of belief, that a family with 2 children has 2 daughters, given that they have at least 1 daughter? Okay, so normally I would stop and get the audience to discuss this until somebody kindly suggests that the answer is 1/3. Well, I guess we can't do that by video, so let's just look at the visualization for how that comes about. So the key takeaway from this is that you have to read statements in probability theory and data analysis extremely precisely to make sure that you interpret them logically correctly. So the question is, a family has 2 children. We're told that they have at least 1 daughter. That's a logical statement. What is our degree of belief that they actually have 2 daughters? So if you want to discuss this in terms of probability theory, you should end up with some sort of understanding that's physically like this. So you could write down a list of the possible sets of children that the couple might have. A boy and a boy and a girl and a boy, or two girls. And you should be able to sketch a Venn diagram of the universe of those four outcomes. And in your model, you might do what I've done in my basic model, and I would say these are equally plausible events. So this is one of the key ideas in probability theory: equal certainty, or situations about which we have indifference, a nice property. We saw last time there was such a thing as a calibration experiment, and we said if we're indifferent between outcomes, the outcomes are we have equal information or symmetric information in support of each outcome, then we say they have equal degree of belief or equal probability. In my example here, I've got 4 possible outcomes for the kids that this couple might have, and I say they are each equally probable. They each have a probability a quarter. Then I get some new information. I'm told that they have at least one girl, and processing this information logically, all that does is it renders one of the outcomes impossible. So we know that they don't have 2 boys, but we've learned nothing we've learned nothing to favour the other any of the other 3 outcomes more than the other. So we have, in this case, we've gone from the old universe, which had 4 outcomes that were equally likely, to having 3 outcomes that are equally likely. And we could either say, well, that means the probability they have 2 girls is then a third, because it's one of the now equally likely explanations, or we could plug the numbers from the starting situation into the conditional probability formula, and we end up with probability of B given A, that they have 2 girls given that they have at least 1 girl. Well, that was the intersection of the 2 cases from my original situation, 1/4, divided by the probability that they have at least 1 girl, which was 3/4 originally. So you process that and you get 1/3. And all we've done there is we've manipulated the concepts of equal certainty or indifference and impossibility. And we've obtained, we can use that to obtain an intuition of what conditional probability is, and we can see that our conditional probability formula is well behaved in terms of how this outcome should work. Good. So this is something that we need to understand mathematically. Let's, before we go on, just say something about data analysis, which I thought this is an aside, so you can skip this, but this is a useful fact in terms of going back to the overinterpretation of data, which I warn you happens all the time in the real world or in the news. Now, here's a map from probably Wikipedia, indicating human sex ratio by country. Countries which are coloured in blue on this choropleth have more females than males. Countries which are coloured in red have more males than females. Countries which are green have the same number to within 3 significant figures. And this is simply amusing because it's a source of... clearly people like to take this and they like to immediately say, well, not only is this some data, but there's a reason for this. And they like to come up with reasons. They like to overinterpret. They say, well, well, these blue countries, they say, by and large, these are decadent westernized countries. They say, well, it's Europe and America, and some of the places that are mostly well off. And they say, well, in these countries, what's happened is there are chemicals in the drinking water, and the chemicals cause there to be more females than males born in these countries. Meanwhile, in the red countries, these include places like China and India, where we strongly suspect there's a sex-selective abortion going on, and people are favouring having male children, which is why you get, and maybe that's true in these other red countries as well, maybe that's why you've got more males than females. Actually, this is rubbish. Both explanations are not... well, it's not impossible that those explanations might be true in some situations, but there's nothing in the data to prove that. Actually, the data is mostly just giving you a map of average age in the different countries. Because contrary to the reasonable assumption I made in the previous slides, that you've got equally likely 50-50 chance of a couple having a boy or a girl, actually, across the world, there's about 1.05 or so boys born per girl. And this is offset by the fact that males have a higher mortality rate at every age than females. So at some point, like, say, the age of about 40 in, say, the UK, you would have the situation that in a particular, a representative town in a school class, if it's well representative, you might have 105 boys and 100 girls at age about 5, say, or that many born anyway, strictly speaking. And by the time they reach the age of 40, you'd be at parity, and you'd have, say, 98 of each, for example. And then at higher ages, you've got many more females than males. So how does this map come about? Well, it's largely a map of average age. When you have countries where you have a mature population, like in the UK, your older population, which is heavily biased towards more females, dominates the entire population average, and so you have a population with more females than males. And the reverse situation when you have countries like India that have a young population, where you've still got that excess of males who were born. So the overall country population is more male than female. So yeah, this is just an example of overinterpretation of a map, which is apparently encouraged just by the way the data is presented. Watch out for that sort of thing. There's no real rule apart from be very careful about going from strict what is the data, what is the sex ratio in each country, the descriptive statistic. Be very careful about going from that to a possibly true conclusion about why it is that comes about. In the rest of the mathematics in this chapter, we'll try and we'll try and stick to cases where we're not going to have such severe problems with this misinterpretation. Anyway, so for the example in 4.5g of how conditional probability is processed, you should be able to follow the slides, see how that plugs into the conditional probability equation 4.5e, and gets you a third for your example of does a family have 2 daughters. Right, the most important manipulation in probability theory is the one that takes the conditional probability formula and uses it to give you Bayes' rule or Bayes' theorem. This is a nice simple bit of maths. Once we've talked about what probability is, which we have now, we said that there is this conditional probability equation 4.5e, and we take this as true. We can write this in a slightly different way. If we just multiply through by the probability of A, we get something called the multiplication rule, equation 4.6a. And the multiplication rule says the probability of the intersection of A and B is equal to the probability of A times the probability of B given A. And then we make one more statement. We say, well, A and B are events or statements which may be true, and we could have considered them occurring the other way around. We could have said that we learn about B first and then consider the conditional probability of A given B, in which case we'd get another expression for the probability of the intersection of A and B, the second line. Because these refer to literally the same list of outcomes occurring, the list of outcomes in the intersection of A and B, those two expressions must be equal to each other, so you get probability of B times conditional probability of A given B is equal to probability of A times conditional probability of B given A. Dividing that through by probability of A, you get Bayes' rule. Probability of B given A is equal to probability of A given B times probability of B over probability of A, or rather than reading that in words, learn to see it as equation 4. I've got written here 4.5c. That should probably be 4.6c. That's Bayes' rule. It is extremely valuable for scientific inference. The next section of the course will be using it to make useful statistical inferences. As I said, where the event B describes some possible hypotheses. These could be predictions or explanations, and A is some data. So, in the next part, we will learn how to draw general purpose inferences using probability theory and Bayes' rule, equation 4.6c, and we'll start the next part by talking about the tools which you need to do that, which are the principle of indifference and the law of total probability, in addition to Bayes' rule. And once you have those, you will be able to make once you have those, you have the comprehensive set of tools needed to do Bayesian inference. And so we'll look then at a particular example of how you do that. Good.